Good afternoon, everyone. My name is Chen Long, and then I'll talk about my PhD work regarding the nucleation scaling studies for flow assurance solutions. So, to start with, the next generation of UW nucleation apparatus, namely PAP Alta or PAP cell, is targeted to experimentally investigating the system size scaling hydrate. And then we confirmed that gas hydrate initial growth rate can be scaled by gas water interface area. And also we found that when we increase the system size by 16 times, the nucleation rate increased about 10 times. So this is another finding for scaling of nucleation. So as Mark mentioned earlier, we have that benchtop scale apparatus, namely the lab data which is in millimeter scales and HPS Alta system in centimeter scales. And we know that in industrial flow lines, there's long subsea pipelines which in kilometer scales. So the question now is how we scale from benchtop to field scale. So the strategy we're trying to use here is system size based scaling, and then hopefully that the newly developed PAP Alta system can be served as a bridge from benchtop scale to the field scale. So we have this unique suite of experimental apparatus. So from the left-hand side, we have acoustic lab data where we can suspend water droplet inside a high-pressure hydrate forming gas phase. So where we don't have any steel contact in there, and we force that hydrate form on the surface of water gases droplet. And in opposite way, for HPS Alta system as well as the PAP cell, we have steel contact with the water and gas. So as these center plus showing, from very small lab data to pipe cell, we have big changes in system sizes gradually. So from which these set of experimental apparatus, we're trying to understand can nucleation rate be reconciled via appropriate scaling techniques. That's what we're trying to find out here. So if I can introduce more about this new developed PAP cell. So the left-hand side picture is showing a PAP cell sitting in the thermal enclosure. The thermal enclosure serves as a so to make that environmental temperature is constant. The right-hand side video here is showing the structure of this PAP cell. So in the middle here is the PAP cell itself, it's a pipe, and then both ends here and there is flames for sealing purposes. And then this component in here, we call it pipe cladding, which provide a flat surface where we can attach the water blocks for coolants and also the thermoelectric elements for temperature control. And here in the middle, we have a insert that is, we call it stirring seat, which hold the magnetic stirrer inside to provide the mixing ability to the entire system. And another two small pieces here is PAP support that can hold the PAP cell on top of the magnetic stirrer. So now I want to talk about more of that unique feature in this PAP cell. So here we're using the thermoelectric temperature control approach, which is same principle as HPS Alta system. And to achieve a better temperature control for these big systems, we have divided this whole system into three sections: left, middle, and right. And each section control the temperature independently. And also, we have multiple thermometers directly inserted into the PAP cell. So that thermometers can monitor the actual fluid temperature. So thanks for that, we can detect hydrate formation. And then we also can detect where the hydrate formed via the temperature signal. And another helpful feature we have here is the ability to vary the mixing speed and location. This feature is going to be extremely helpful when we're doing sub-in and start-up simulations. Here is temperature time plot. This is as one cycle of induction time experiment. The system cooling down from the high temperature to a target temperature, and we hold the temperature until the hydrate formation is detected. So even this is a big system. The temperature inside is well controlled. The differential between fluid thermometers is less than 0.2 Kelvin. And here we are showing the pressure time series data plot, which is corresponding to left-hand side temperature plot as well. So in one induction time cycle, the system can experience 3 different phases. First will be the cooling. So corresponding to that temperature plot, the pressure is reduced to until that system hit the target temperature, and then having the pressure plateau, which is the induction time period. And once the hydrate formation is detected, it goes to growth stage. So the hydrate detection is based on the sudden pressure drop, as we can see in here. So that is indicating there's a hydrate formation. And as I mentioned earlier, that we have fluid thermometer inserted into fluid. So the temperature signal here, the sudden increase of that temperature signal, which also coincides with that pressure drop, which also can indicate the hydrate formation. Right. So with that in mind, now I'm going to go through that how we experimentally investigating the size scaling. So first, I will start with the initial growth rate. So the initial growth rate is based on the first 0.5 bar pressure drop immediately after hydrate formation. So what we measure is we measure that time that takes to have 0.5 bar pressure drop, and then we do some calculations, and then gathering all that data together, and we will have an average growth rate in each system, just like the plot showing here. So here, the blue triangles, those are the growth rate from HPS alpha system, while the diamond, this part, is from the power cell. So apparently, we can notice that the growth rate in path alpha is faster than HPS alpha systems. And we know that initial hydrate growth rate prefers to occur on the gas-water interface area, as we observed in the levitated water droplet. So apparently that in this case, there's nothing, nowhere else we can form hydrate and growth. It's just happening on the water gas surface area. Hey. And here, even in the hydrate reactor with the stainless steel, the hydrate form, and then it's cover the water gas interface area, and then grows on that. So what if we scale that growth rate data we have, and then if that can line up together? So that's what will happen when we scale those growth rate based on the gas-water interface area of each system. Those growth rate actually here can line up well. And then we fit either a linear fit by constraining the intercept at 0K subcooling. So here we confirm that scaling of growth rate working with the gas-water interface area. So now I'm going through that scaling of a nucleation rate. So as the induction time experiment, one hydrate cycle, we have one induction time data, and we repeat that hydrate cycle again and again, and they get a lot of data of that induction time. And with that, we pin those data together and then form a histogram like showing here. And from there, we numerically integrate that histogram to construct a cumulative hydrate formation probability, or we call it CDF. Probably you have seen this plot a lot of times. So this is that CDF in HPS alpha system. All induction time data distributed exponentially very well. And what happened in the much larger path alpha system? So here we still observe the same trend. Induction times remain exponentially distributed even in the larger path alpha system. So now we have this induction time data. So how we extract the nucleation rate from this CDF? Now, as Mark explained this equation earlier, so here the P is formation probability, and J is nucleation rate, and T here will be the induction time. So we feed that equation to our CDF, and then set the nucleation rate as the only variable, and then we extract the nucleation rate from the basket of the CDF. So that's how it looks like when we have all the extracted nucleation rate plotted together. So same, the blue triangles here are the nucleation rate from HPS delta, and the diamonds from alpha system. So the question, we have the nucleation rates now, and then the question now is how we test the size scaling. Well, when you look at the nucleation rate, the PAP cell always have higher nucleation rate when compared to HPS delta. If you want to achieve this similar nucleation rate, HPS alpha system have to go higher subcooling. And also at 5K subcooling, at the same 5K subcooling, the nucleation rate of PAP alpha is about 1 order of magnitude higher than HPS alpha system. So how we test the size scaling? So here is a diagram or an example that when the PAP cell have 100 ml of liquid loading, the gas-water interface area is around 185 square centimeters, while the three-phase line is about 1.2 meters. What if we change that liquid loading to 300 ml? So the area changed to 111 square centimeters, while the three-phase line is remain almost the same. The actual change is less than 0.2%. So with that case in mind, now we have different cases of different system sizes. So we consider the gas-water interface area and three-phase contact line, which will be the most potential will be the most appropriate system size. So now the question is, which one is the better system size for nucleation scaling? But the idea is simple. So this equation is nucleation rate equation from nucleation theory, which is simply the function of temperature-related subcooling. And the idea with scaling is divide this equation both sides by the system size, and then we will have that scaled nucleation rate, and then we see if that all the scaled nucleation rate can line up together or reconcile. So keep that equation in mind. But I'm going to go through the first case. So here we're comparing from alpha system to PAP cell. In this case, both sides, both the gas-water interface area and three-phase lines are increased by a factor of 16. And then we're going to do this scaling with this equation. And first, we'll try the gas-water interface area. And it turns out all the scale of the nucleation rate can fit well with the nucleation rate equation, which works well. And then it turns out, what if we try the three-phase line? So with three-phase line, it's showing the similar results, and then cannot really differentiate these two, which is better, which is worse. So here, I like to say nucleation rate can probably be scaled by the gas-water interface area, and all the three-phase line from HPS alpha system to PAP cell. So it makes sense because both system size both increase with a factor of 16, and whichever you choose to scaling, it works similarly. And another interesting case is here. So now the three-phase line is remain the same, but the surface area is changed by a factor of 2. So the nucleation rate plot in these two cases is showing here. So the pink diamond is the one case that have a higher gas-water interface area, and then if we scale them with that gas-water interface area, they actually the scale nucleation rate is actually overlapping on top of each other, and fit down with the CNT equation. So here, the gas-water interface area is a more appropriate system size for scaling between pipes, between similar pipe or similar geometries. Now, so in terms of way forward, let's say the nucleation rate scaling with gas-water interface area in the well-mixed system, just like our HPSL system as well as the PAP cell. And the fact of the flow region or shear rate or in-channel water that is still remain unknown to the system scaling. So now I think we're trying to focus on the near future will be in a startup simulation. So here we can manipulate the mixing of the system, so we can try to investigate that formation probability dependence on the turbulence level. So together with this new result, we hopefully can inform a more comprehensive formation likelihood in the flow line in the near future. So to wrap up this talk, so PAP cell is experimentally investigated system size scaling, and we confirmed that gas-water interface area scaling of hydrate initial growth rate works well, and then confirmed that candidates of interface test for nucleation scaling in different cases. Okay, so thanks for the ARCF funding, and then thanks for my supervisor, Pete, Ari, Bruce, and Zachary for help providing. Thank you.